Water scarcity is a significant challenge in Brazil's semi-arid regions, where annual rainfall averages around 500 millimeters. Many families rely on unreliable government water trucks or struggle with limited access to clean water. To address this issue, Inaugurated began conducting workshops in 1999 in Minas Gerais and later expanded to different regions, including Sarapidica in Rio de Janeiro. My goal is to demonstrate an effective and sustainable solution for rainwater harvesting: plate cisterns. This technique has been successfully implemented in semi-arid regions of northern Minas, Ceará, UECE, and Bahia, providing families with a low-cost, long-term solution for clean water storage. Plate cisterns offer a sustainable method for collecting and storing rainwater for household use, including drinking and cooking. This technology is particularly beneficial for small-scale farmers who lack access to drilled wells or public water systems. By adopting this method, families can achieve greater independence, improve their quality of life, and reduce their reliance on external water sources. In the construction of plate cisterns, a unique method is used to create the concrete walls. Instead of conventional precast molds, the walls are printed manually by shaping wet concrete in a specially prepared mold. This mold is formed on a sand surface, which allows easy removal once the concrete sets. The use of sand as a base prevents the concrete from sticking, making the lifting and assembly process more efficient. This technique is not commonly used in traditional construction, but has proven to be highly effective for building durable and cost-efficient water storage tanks. Every part of the cistern, including its walls and roof, is made on-site using locally available materials. The walls are cast separately in manageable sections, which are then assembled and reinforced with steel bars and cement. This self-sufficient approach reduces dependency on expensive prefabricated materials, making the construction process more accessible for small-scale farmers. The process of making concrete pillars for the plate cisterns begins with the preparation of a sturdy mold, which is usually made of wood or metal. The mold is designed to hold the concrete mix in the desired shape and size, ensuring that the pillars are strong enough to support the structure of the cistern. Before pouring the concrete, steel reinforcement bars, rebar, are placed inside the mold. These steel bars are essential for adding strength and durability to the pillar, preventing cracks and structural failure over time. The rebar is carefully arranged to ensure even distribution throughout the pillar, often tied together with wire to maintain its position during the pouring process. Once the mold and steel bars are set, a concrete mix consisting of cement, sand, gravel, and water is prepared. The mixture is poured into the mold, ensuring that it completely covers the steel reinforcement. To remove air bubbles and ensure uniformity, the concrete is compacted using a vibrating tool or by tapping the mold. After pouring, the concrete is left to cure for several days, allowing it to harden and gain strength. Once fully set, the mold is carefully removed, leaving behind a solid concrete pillar ready for use in constructing the cistern's frame and roof support. The construction of the main foundation of the water tank is a crucial step in ensuring the stability and durability of the cistern. The process begins with selecting a suitable location, ensuring the ground is level and free from debris. A circular trench is then dug to mark the cistern's perimeter, providing a stable base for the structure. Next, a mixture of sand, cement, and gravel is prepared and spread evenly across the base to create a solid foundation. Before the concrete is poured, a steel reinforcement frame is installed. This steel frame consists of interconnected steel bars, arranged in a grid-like pattern, enhancing the foundation's strength and preventing cracks over time. Once the steel frame is in place, the concrete mix is poured over it, covering the reinforcement entirely. The surface is smoothed and left to cure for several days. This strong foundation supports the cistern walls and ensures the tank can withstand external pressures and weight from stored water. The installation of the tank walls is a crucial phase in constructing the plate cistern, as it ensures the structure's strength and longevity. The process begins with carefully placing pre-made concrete plates around the foundation. These plates, each measuring approximately 60 centimeters in height and 50 centimeters in width, are positioned vertically to form the curved walls of the cistern. To ensure proper alignment and spacing, a small gap is left between each plate. These gaps allow for the placement of a cement mixture that binds the plates together, creating a seamless and watertight wall. Before filling the gaps, a layer of mortar is applied to the edges of each plate to improve adhesion and prevent leaks. Once all the plates are set in position, the gaps between them are carefully filled with a high-quality cement mixture. This step is done gradually, allowing the cement to settle and bond securely with the plates. A leveling tool is used to check the uniformity of the structure, ensuring that all walls are evenly aligned. After the cement has been applied and smoothed, the walls are left to cure for several days. During this time, occasional water sprinkling may be done to prevent cracks from forming. Once the walls have fully set, additional reinforcements are added, such as a steel frame around the exterior, to further enhance durability. After the cistern walls have been installed, additional steps are taken to reinforce the overall structure and ensure durability. The foundation floor, which was initially laid with a concrete mixture and steel reinforcement, is further strengthened with an additional layer of casting. Simultaneously, the inner walls of the cistern undergo reinforcement. A smooth plaster layer is applied to the interior using a cement mixture, ensuring the walls remain strong and watertight. This step is crucial in preventing seepage and maintaining the quality of stored water. The interior surface is also carefully leveled and smoothed to minimize rough areas where dirt and algae might accumulate. Externally, a steel frame is constructed around the tank, wrapping around the outer walls. This frame consists of steel bars or wire mesh, which provides additional support and structural integrity. The steel reinforcement prevents the walls from expanding or cracking under pressure, especially when the cistern is filled to capacity. The installation of the water tank cover is a crucial final step in the construction process, ensuring the stored rainwater remains clean and protected from contamination. The cover is designed to be strong, durable, and well-fitted to prevent external elements such as dust, insects, leaves, and small animals from entering the cistern. Before installing the cover, concrete pillars are strategically placed around the tank to serve as the main frame, providing structural support. These pillars are made using a mold filled with a cement mixture reinforced with steel bars for added strength. Once the concrete has cured and hardened, the pillars act as a stable framework to support both the tank and its roof. Their purpose is to ensure the cistern remains secure, even under harsh environmental conditions. The cover is typically precast in a separate mold, shaped to fit the exact dimensions of the cistern opening. It is made using a strong cement mixture, reinforced with steel mesh or bars to enhance durability. The mold is designed with slight curvature to prevent water pooling on top, reducing the risk of cracks and weather-related damage. Once the cover is fully cured, it is carefully lifted and positioned onto the top of the cistern, ensuring a tight fit. Cement mortar is applied around the edges to seal any gaps and provide extra stability. Some covers include a small access hatch or inspection hole, which allows for easy maintenance, water quality checks, and treatment. After the initial construction, the outer wall of the tank is reinforced with an additional layer of cement to enhance durability and prevent leaks. This layer strengthens the structure, protecting it from external damage and environmental factors. Similarly, the roof is tightly covered with cement to create a solid, sealed surface that prevents contaminants from entering. This final coating ensures the longevity and efficiency of the rainwater storage system. The Maharashtra Institute of Technology, MIT, at the Rajbagh campus in Pune, Maharashtra, India, is home to the world's largest dome, a monumental structure that stands as a testament to the harmonious blend of spirituality, science, and architectural prowess. This dome, officially known as the philosopher Saint Shri Dnyaneshwara World Peace Prayer Hall and World Peace Library, embodies the universal ethos of Vasudhaiva Kutumbakam. The world is one family. visionary behind the monument, the inception and realization of this architectural marvel are credited to Professor Dr. Visvanath D. Karad, a distinguished educationist and the founder of MIT. Driven by a vision to foster a culture of peace and deliver value-based universal education, Dr. Karad conceptualized this dome to serve as a beacon of knowledge, spirituality, and global unity. Architectural grandeur: the dome boasts impressive dimensions, with a diameter of 160 feet and a height of 263 feet, surpassing notable structures like the St. Peter's Basilica in Vatican City, which has a diameter of 136 feet and a height of 448 feet, supported by 24 massive columns, each standing 63 feet tall. The dome encloses a space that can accommodate over 3,000 individuals, making it not only the largest in diameter but also a significant gathering place. Design and symbolism: the dome's design is rich with symbolic elements that reflect a confluence of various disciplines and philosophies. Meditation center: at the heart of the structure lies a meditation center designed to align the 7 chakras of the human body, promoting holistic well-being and spiritual enlightenment. Pillars of significance: the dome is supported by 24 pillars, each representing different branches of science that define and steer life, including physics, chemistry, mathematics, and geography. Beyond these, there are additional pillars symbolizing domains such as music, drama, art, and culture, embodying the holistic nature of human knowledge and expression. Bronze statues adorning the interior are 54 larger-than-life bronze statues of revered saints, scientists, philosophers, and spiritual leaders from various cultures and eras. This includes figures like Gautama Buddha, Jesus Christ, Mahatma Gandhi, Albert Einstein, and Aristotle, symbolizing the unity of diverse wisdom traditions under one roof. Construction journey: the construction of this monumental dome spanned 13 years, culminating in its inauguration on October 2, 2018, coinciding with the 150th birth anniversary of Mahatma Gandhi. Notably, the construction process did not involve the use of cranes. Instead, mini lifts and cuplock systems were employed, showcasing innovative engineering techniques. Inauguration and dedication: the inauguration ceremony was graced by India's Vice President, M. Venkaiah Naidu, who lauded the structure as a monumental addition to the thoughts propagated by the great saints of Maharashtra. He emphasized that the dome symbolizes harmony and peace, inspiring a sense of unity and humanity in every individual who enters its premises. Purpose and vision: the World Peace Dome serves multiple purposes. Educational hub: the World Peace Library, encompassing an expanse of 62,500 square feet, stands as a testament to the knowledge and wisdom that India as a country holds and disseminates. Cultural confluence: by housing statues of luminaries from various cultures and disciplines, the dome fosters an environment of intercultural dialogue and mutual respect, embodying the principle of Vasudhaiva Kutumbakam. Spiritual sanctuary: the meditation center within the dome offers a serene space for individuals seeking spiritual growth and inner peace, aligning with the universal quest for harmony. Global significance: the World Peace Dome stands as a living heritage of harmonious amalgamation of Eastern spiritual peace and Western scientific wisdom, exemplifying the ethos of Vasudhaiva Kutumbakam. It serves as a center for wisdom, knowledge dissemination, and social transformation, aspiring to educate the masses and help in establishing a harmonious and peace-loving society. Visitors to the dome can immerse themselves in an environment that seamlessly blends architectural splendor with profound philosophical and spiritual symbolism. The presence of the 54 bronze statues offers a unique opportunity to reflect on the contributions of these luminaries to human civilization. The meditation center provides a tranquil space for introspection, while the library serves as a repository of knowledge, accessible to scholars and the general public alike. The world's largest dome at MIT's Rajbagh campus is more than an architectural feat. It is a manifestation of a vision to unify humanity through the convergence of science, spirituality, and philosophy. It stands as a beacon of peace, knowledge, and unity, inviting individuals from all walks of life to experience and contribute to a harmonious global society. The 2019 Seminarweek at ETH Zurich was an immersive and hands-on exploration of innovative concrete construction techniques. Under the theme Concrete Space, participating students had the unique opportunity to engage in the design and construction of a remarkable concrete shell structure on the ETH Hongerberg campus. The project not only tested the students' theoretical understanding but also provided invaluable practical experience in materials, formwork, and construction methodologies. The primary objective of this seminar was to construct a thin shell concrete structure using advanced formwork techniques. The chosen method combined two innovative approaches, hanging formwork and pneumatic formwork, both of which exploit natural forces and controlled inflation to create elegant and structurally efficient geometries. These methods, which have been developed and refined through research in structural engineering, allowed for the creation of a lightweight yet robust shell that would have been difficult to achieve with conventional formwork. The shell was constructed using reinforced concrete, specifically Sika monotop, a high-performance concrete mix known for its strength and durability. The dimensions of the structure were as follows: long sides 8 meters, short side 7 meters, height 3 meters, thickness ranging from 4 centimeters to 12 centimeters, total weight 4 tons. These parameters ensured a structure that was both visually striking and structurally sound, balancing material efficiency with spatial effectiveness. Before the physical work began, students collaborated in groups to design the shell's shape, taking into consideration material constraints, structural integrity, and aesthetic ambitions. The principles of hanging models, often used in historical shell design, such as those pioneered by Antoni Gaudi and Heinz Eisler, were a key source of inspiration. The hanging formwork method involved suspending a flexible membrane or net onto which the wet concrete was applied. Gravity naturally shaped the membrane into an optimal form, minimizing bending stresses. The pneumatic formwork relied on an inflatable structure that provided temporary support while the concrete was being applied and set. This method allowed for a quick and efficient construction process. Reinforcement placement. To ensure structural stability, a carefully planned reinforcement mesh was embedded within the concrete. This reinforcement not only increased load-bearing capacity, but also helped control cracking, ensuring longevity and durability. The specially formulated Sika monotop concrete mix was carefully applied onto the formwork. Given the varying thicknesses, precision was required to maintain the structural and aesthetic integrity of the shell. After application, the concrete was allowed to cure over several days. Proper curing was essential to achieve the desired strength and to prevent shrinkage-related cracking. Formwork removal and final adjustments. Once the concrete had sufficiently hardened, the formwork was carefully removed to reveal the final shell structure. Minor surface refinements were carried out to enhance the visual quality and structural performance of the shell. Challenges and learnings. Throughout the process, students encountered and overcame various challenges. Material behavior. Achieving a consistent and smooth surface required precise control over the concrete application process. Structural efficiency. The team had to ensure that the formwork methods created a shell capable of supporting its own weight while maintaining a thin, elegant appearance. Time constraints. Given the Seminarweek's limited time frame, meticulous planning was essential to complete the construction efficiently. Despite these challenges, the project successfully demonstrated the potential of combining traditional construction wisdom with modern materials and techniques. Students gained a deeper appreciation for the complex interplay between design, engineering, and materials science. Impact and reflections. The completed concrete shell stood as a testament to the collaborative efforts of the seminar participants. It was not merely an academic exercise, but a real-world demonstration of how innovative thinking can lead to sustainable and efficient construction. The knowledge gained from this experience will undoubtedly inform the students' future endeavors in architecture and structural design. The Seminarweek Concrete Space 2019 was a resounding success, pushing the boundaries of what is possible with concrete construction and reinforcing ETH Zurich's reputation as a leader in architectural innovation and engineering education.